Hey, it seems like it's been about a million a million years. Um, so hyperbolas, which is the we had not gone over, I had not gone over yet, is 11.4. So 11.4 from the textbook, and there's a lot that can be said about hyperbolas. And again, the top we're not going to exhaust the topic. We're not going to talk about everything, by by a long shot. We're not going to talk about everything that there was to talk about hyperbolas. They're a conic section. And if you look in the book, you'll see a very simple to see picture of where they come from in terms of conic sections. Now, where you find them in the real world. So I guess if you look around you, you'll see straight lines everywhere. You'll see circles. So those are fairly easy to find. Parabolas, throw an object in the air, a dense object and not too fast so you can neglect wind resistance. Or look at the water coming out of a water fountain. There's a parabola. Or the cross section of a mirror in a telescope, or the cross section of a radar dish, satellite dish. So yeah, you can find parabolas all around you in everyday life. Ellipses are a little more difficult. Um, it turns out the planets do go around the sun in elliptical orbits, but you can't see that. Even if you went outside the plane of the solar system and looked down upon the solar system, or the disk of the solar system, or the disk which is traced out by the planets going around the sun, for example, the Earth's orbit would still look circular. There's a way to measure how eccentric these orbits are. It's called the eccentricity. We didn't do that. We're not going to do that. But the Earth's orbit is elliptical, but it's not very eccentric. It's not very elliptical. It's almost a perfect circle. Um, so as far as finding ellipses in everyday life, that's not so easy to do. Uh, One place is, for example, I forgot, there's a room within the Capitol building in Washington, and there's lots of other ones like this, which have an elliptical roof. And if one person stands at a focal point and another person stands at the other focal point, all the sound waves will reflect. Well, when they travel from the one speaker's mouth, they'll all reflect to the other focal point, and you hear that person, even if they're whispering, and they're called whisper gallery. I believe that was due to Thomas Jefferson. There's a device called a lithotripter, which you can find at some hospitals where they emit ultrasound from one focal point. So here's one focal point. Here's the ellipse, and all the sound waves from this converge on this other point, and you place the patient in the machine, the device. So, for example, a kidney stone, and it will fracture the kidney stone so the stones can pass out. Now, what the heck is a hyperbola in terms of maybe something that you see in everyday life? And this, I have a much more difficult time finding any example where I could say, well, just take a look at this. I'll give you a classic example. Suppose we have an object, and I'd like you to think of this object in space. I don't know, the Earth, the sun. Although really, I just really want you to think of it as a point object, but just think of it as an object. And from a great distance, tremendous distance, here we have this object moving through space. And if you think of this object as being, how should I put this, remote or in deep interstellar space, it would be moving along a straight line. Now, what is meant by a straight line, and is that really true? Well, the answer to what is a straight line, that's a deeper question than it might sound like at first. And is it really moving along a straight line? The answer really is yes, but then it depends on what your definition of straight line is. Okay, but let's put all that aside. This is moving along a straight line. Now, what happens when it gets close to this object? Well, imagine it's going like this, and as it gets closer and closer, the force of gravity starts to increase, and it increases the square of the distance, but we don't need to worry about that. But the path of the object will look like this. And roughly speaking, it's fairly curved here, and it's fairly straight here and here. And this turns out, if I make a duplicate of this curve, if I make a mirror image, if I did something like this and I made a mirror image over here, the resulting object would be a hyperbola. Now, granted, this isn't something you can, like, quote unquote, see. You can't go outside your window and see this occur. But nonetheless, this you could, in your mind's eye, if you will, you could imagine this is hyperbola. So if you had an object coming into our solar system from interstellar space, um, and it was shot along a straight line, it would follow the path of a hyperbola. Here's another example which you can't really see, but it really is an everyday sort of thing, and that's in a PET scanner, positive emission tomography scanner. So if you want to know more details, look at a PET scanner, not a CAT scanner, not an MRI, but a PET scanner. Sounds kind of funny, doesn't it? Like you scan your PET, I don't know. Okay. But what happens is if you send in a positively charged particle, like a proton, but it doesn't have to be a proton, but say an object, an atomic sized particle, or some atomic sized particle with a positive charge. And let's say over here we had a negative charged object. And let's just say that relatively speaking, this has a tremendous mass compared to this one. So maybe this is a proton and this is a negatively charged, let's say, molecule. If you fire this proton in on a relatively straight path, when it gets close to this negative charge, it will be attracted to it, and it will follow this hyperbolic path. So within a PET scanner, if you could get down to this size here, you could see hyperbolas, and you can see objects following hyperbolic paths. Okay. Now, what's the conic section definition of a hyperbola? Well, it's you're given 2 points, and it's a collection of all points such that this distance, remember with an ellipse, it's the sum of the distances. But with a hyperbola, we make it the difference of the distances. So this is equal to some constant, I'll say L, like the length of a string. You can't draw this the same way you can draw an ellipse. You might wonder how on earth could you actually physically draw a hyperbola. We don't need to worry about that. And not only that, but we're not going to worry about all the algebra that leads up to the equation of ellipse. Instead, we're just going to do what the textbook does. And we're going to short circuit all that. And we're going to go right up to this idea right here. That if you have this, that's the equation of ellipse. And what does it look like when you graph it? Well, hey, before I graph it, well, let me just say, roughly speaking, it's going to look like this. And I'm sure you've probably seen this sort of thing before, where these are the 2 branches of the hyperbola. So this together with this, that is the hyperbola. And each one of these is a branch of the hyperbola. But I would like you to consider a couple of things. Number one, there's no y-intercept. Now, how would I know that right away? Hey, let's do a really, really, really concrete example for a second. Let's make this 2. Let's make this, it doesn't really matter here, but let's make this a 2, and let's make this a 3. So this would be x squared over 1/4 minus y squared over 1/9. We'll make this really concrete. Now, how do you find y-intercept? You make x equal to 0. Say you make x equal to 0. What happens here? This becomes 0. Look at that resulting equation. What would that resulting equation look like? Y squared over 9, negative, and that's important, equals 1. Let's multiply both sides by -9. You get y squared equals -9, and you get y equals plus or minus 3i. Well, that doesn't make any sense given what we're doing. So we're making a graph of y as a function of x. This x-axis, these are real numbers, not complex numbers, not imaginary numbers. This axis, this is the y-axis. These are real numbers, not complex numbers, not imaginary numbers. This is a complex number. It doesn't really make it does not make any sense in this context. Whew. So what does all that mean? It means there are no y-intercepts. Because if we're not using complex numbers, this has no solution, this has no solution, so there's no solution. So, like I said, there are no y-intercepts. And if you believe the picture that I drew, you would have said right away, well, I could just look at it and tell you there's no y-intercepts, and so there aren't. What about x-intercepts? How do we find x-intercepts? We set y equal to 0, because we're not above or below the x-axis. If I set this equal to 0, what do we wind up with? X squared over 4 equals 1. So x squared equals 4, and x equals plus or minus 2. And so, in fact, the picture would look like this. 1, 2, 1, 2. And everything sounds pretty good so far. In other words, everything seems consistent so far. And there's something nice about this. Look, see this number right here? That number right there, which we normally will call A, that will give us our x-intercepts. There won't be any y-intercepts, but that will give us our x-intercepts. Now, I want us to consider something else. Remember I mentioned, and I'm just saying take this on, I don't want to say take this on faith, but nonetheless, I'm basically saying, hey, take my word for it, or we're putting this off for further study. But remember the idea of this object coming in from deep, deep interstellar space, where it's essentially not under any gravitational influence, so it's following a straight, any point gravitational influence, but it's following a straight path. And then as it gets near an object, it starts to, what it actually does is it accelerates when you change direction or velocity or accelerate. But it's changing direction, and it starts to do this. The idea is if you're far, far away, you're basically on a straight line. And here's what we want to do. We'd like to consider this equation right here. Let me just erase this for a minute here. Consider this equation right here when we're really far away. Well, really far away from what? Well, it's really the focal points. But really far away would mean really large values of x. So what I want to do first is I want to solve this for y. So let's solve this for y. We would get this term over here and one over here, and we wind up with this. We get this over there and this over here, so x squared. And then I flip sides. But hey, fill in the details. Make sure you see how you got from here to here. Let's multiply both sides by this term here. Okay, so y squared equals 3 squared over 2 squared. Again, you should probably wonder, why am I not just writing this like 9 and 4? We'll just hold on to that thought for a second. X squared minus 3 squared. Now, what I'd like you to do is I would like you to, here, let's even go one step further. Sorry about that. Y squared equals the square root of consider x having a very large value. What would be a large value right here? Well, how about 100? How about 1,000? How about 1 million? How about a billion? How about a billion raised to the power of a billion? Just imagine x is 1,000. What's 1,000 squared? A million. This is 9 over 4, so it's what, 2 1/4? So that would be about 2 million. Roughly speaking, what's 2 million minus 9? Well, very roughly speaking, it's about 2 million. Now, what if x was a million? What's a million squared? Well, it's 10 to the 6 squared, so it's 10 to the 12. That's a trillion. That's a 1 with 12 zeros after it. So this is about 2 trillion. What's 2 trillion squared minus 9? Well, come on. Like if you had $2 trillion and someone took away $9, is that really going to affect anything? No. So what this means is for very large numbers, for very, very large numbers, this term right here, we can ignore that term. Now, if we ignore that, so I should put an approximation, like y squared is approximately, not y squared, y is equal to that. Y is approximately equal to that, but it's going to be extremely close for large values of x. Well, I can simplify that now. And I would say y is equal to plus or minus. Now I can take the square root of all that easily. We'll get 3 over 2 x. Well, that's pretty nice. This, one at a time, that's the equation of a line. The slope is 3/2. The y-intercept is 0. And that's the equation of a straight line. The slope is 3/2, and the y-intercept is 0. So what does that mean about our hyperbola? Here's what it means. I said it looked roughly like this. And I kind of said take my word for it on that. But at any rate, here's the y-intercept. What did we say the y-intercept was? A comma 0. And here, the x-intercept, sorry. Did I just say y-intercept? So negative a comma 0. And if we go really far out here, really far out here, the hyperbola almost becomes a straight line. It forms what's called an asymptote, or it has asymptotic behavior. And that just means it becomes more and more and more and more and more like a straight line. What straight line? This straight line. Or, if we're going this direction, this straight line, y equals negative 3 halves, sorry, x. Now, we can summarize this, and let me summarize this. For a general hyperbola, let me erase all this. And we'll go back to the general hyperbola. Again, what I'm saying right now, there's nothing new, there's nothing novel about this. This is exactly what's said in the textbook. And it's what anybody would tell you. I mean, this isn't new. But if we take this, x squared over a squared minus y squared over b squared equals 1. Now we can tell something about how to graph this, or what it looks like. If we go out here, this is going to be the x-intercept, or one of the x-intercepts, a comma 0. And over here, negative a comma 0. The parabola very, very roughly is going to look like this. There's one branch. There's the other branch. And it's going to asymptotically approach these two lines. And what two lines are they? It's funny, that derivation doesn't take very long. So I feel like I'm sort of constantly forever forgetting what these two are, and I'm just redoing the derivation in my head. But at any rate, b over ax and y equals negative b over ax. So if you're given the equation that looks like this, well, you can get a pretty good graph of it, almost like that, right away. Because you can get the x-intercepts. You know there's no y-intercepts. You can easily graph these two lines. Like in the last case, what did I say in the last case? A was 2 and b was 3. Well, you could graph a line that looks like y equals 3 halves x. Slope is 3 halves, 1.5. So graph this line and graph this line, and then just fit the hyperbola in there. Okay. So let me do an example of that. Let me go ahead and do an example of that. So the example of that, let's see, let's take this. How about x squared over 25 minus y squared over 9 equals 1. Now the reason I'm choosing 25 and 9 is because, well, I'm going to be taking the square root of them. So I really want those numbers to be perfect squares. They don't have to be. You know, it just makes for a nice example. And how would we go ahead and graph this? Well, what's the square root of this 5? So 1, 2, 3, 4, 5. Put a dot there. 1, 2, 3, 4, 5. Put a dot there. And then I'm going to graph the following two lines. Y equals 5 over 3. Square root of 25 is 5. Square root of 9 is 3. This and this. We want to graph those two straight lines. Look at this one right here. What's the slope? 5 over 3. Right, slope is rise over the run. So if you go over 3, you go up 5. So go over 3, 1, 2, 3, up 5, 1, 2, 3, 4, 5. And similarly, over here we go over 3 and go down 5. So 1, 2, 3, 1, 2, 3, 4, 5. And let me do something the book does, and honestly most books do too. They tell you to make this rectangle. That's really not a mandatory thing, but almost every book I've ever seen wants you to do this. And I think it's a reasonable thing to do. We can go over here 1, 2, 3, 1, 2, 3. Because similarly over here, well here if I go negative 3, if I make the run negative 3, well since the slope is negative, that would mean the rise has to be positive. So if we go 3 this way, we have to go 5 up this way. So I don't think I went 5 up this way here. So 1, 2, 3, 4, 5. And then here over 3, 1, 2, 3, 4, 5. And we get this rectangle. And then through this rectangle, I should have made that maybe dash line like this. Because you know what? This asymptote is actually not part of the hyperbola. It's not part of the hyperbola. But the hyperbola looks like this. And then again over here like this. And like I've said many times, if you go to Desmos or any graphing software, you get very nice pictures. If you look in the book, you get very nice pictures. if I was going to make a very nice picture by hand, I would use a piece of graph paper, and whatever I did here, I would do it on a piece of graph paper, and I would be much nicer, right? I would go over 3 blocks and up 5 blocks, and over 3 blocks and down 5 blocks, and I would go over 5 blocks here to get the x-intercept, and then I would fit this curve within those constraints, and I would get a much nicer looking graph. Okay, this is the essence of hyperbolas. And please read, was it again, 11.4? Because it's not a great leap that when you go from there to this, let's say right here I said minus 1 squared, and let's see here I said plus 2 squared, that that is the same hyperbola, we've just shifted it. We've taken this exact same hyperbola, almost like, click and drag, and we've shifted it to the right one and down 2. So that's exactly similar to shifting ellipses around. So there's nothing particularly different, or for that matter, any graph. So you can read up on that, but the main thing is to be able to make this original picture right here, to be able to do that, or to understand that. Again, hyperbolas, it seems like a bit of a crazier, more exotic concept. They do exist. They do have practical applications. They are around you. They really are. I mean, things, charged particles pass through you all the time. They follow hyperbolic paths. We just can't see them with our eyes. So hyperbolas are around us all over the place. We just can't see them without some aid of technology. All right. Now, from here, we're going to go into the final chapter, which is chapter 12. We're not going to do the whole chapter. And that's going to seem like a very, very different topic. Some of you might have seen this before. Fine. They're called sequences and series. And again, it really will seem like a completely different topic. And for our purposes, it kind of really will be a completely different topic. And so whether that's good or bad, I don't know. I'll leave it up to you. I believe I haven't looked at all the details yet of chapter 12, but normally within any textbook, you could do chapter 12 almost. I could have done it first. I could have done chapter 12, at the start of the course, or in the middle of the course, or at the end of the course, because I really won't have any major tie-ins to the rest of the course. It will eventually, if you pursue mathematics, there'll be absolute tie-ins to everything, but it just, for our purposes here and in this course, it won't seem like there's tie-ins. Okay, hey, hope you had a good Christmas and New Year's and all that kind of stuff, and hope everybody that is healthy and happy. And all right. So for now.